All right, folks, we'll work here. This is the 6.3 lesson. Now, these ratios that we're going to work with, if these confuse you or if you're feeling a little uncomfortable with those, or when we start working with a unit circle, how in a unit circle, the sine of theta is equal to y and the cosine of theta is equal to x. If you're a little bit confused or uncomfortable with either of those ideas, if you do not feel like a master of those ideas, then go check out the pre-video for the 6.3 lesson because that can help you out. But if you are feeling comfortable with those ideas, if we're using a unit circle, then the sine of theta can be given by the y coordinate at any point along the way. Our cosine of theta can be given by the x coordinate at any point along the way. If that's the case, then our xy coordinates for any point along our unit circle, and that's the key, this is only true for a unit circle, can be given by the cosine of theta and the sine of theta. Now, if we're considering, let's take a look here. I think it will allow me to open it up. Fantastic. We're opening up our GIF here. So when we are working right here, then we can look at any point along the way. We have our dot heading around the circle, right? We're looking at different coordinates here. And we have plotted here along the bottom half. We have plotted our... Let's see if it does let me erase that. Fantastic. We have plotted just the y coordinate. So you can see as our point goes around this unit circle, then you can see how only the y coordinate is being plotted here. And that makes sense because the y coordinate we just went over is equal to the sine of theta. So what that means is what's actually being plotted along the way here is the sine of theta. So at any single point, and I may sound repetitive and that's okay, at any single time along the way, okay, so right about, if it allows me to pause, it does not, that's okay. If I consider the point right here along the side, then right here along the side, this also gets transformed. So the x coordinate of this point along the circle is being plotted here along this graph, what we call the cosine of theta. Now you may find this GIF particularly useful. If you do, you can just Google nice and easy a sine function GIF and it'll pop up for you. Now that's all well and great. We can use that. We know what shape we're expecting because if you're in this course right here, this is grade 12 advanced functions, then you already took grade 11 functions, and in grade 11 functions you recognized these shapes. At that point you were working in degrees, now we're working in radians, but the shape is still the same. Now we're going to use these ideas, this idea of a unit circle, for a unit circle, your x and y coordinates are equal to the cosine of theta and the sine of theta, and we're going to use our special triangles. Now you should be a master of your special triangles at this point. If you are, great. If not, then take this point, and actually either way, take this point as an opportunity to practice your special triangles. In your note right here, I expect you to have both special triangles written not in terms of degrees, obviously in terms of radians. That's how we're working in here. And pause the video, try that out, and then unpause when you have that finished. Fantastic. So we should be working here with these two special triangles. Oops, I forgot to label. Actually, it looks like my labels disappeared, so I'm not sure where they went. These remaining angles. And you should be a complete master of these by now. When you are sitting down to write an assessment, you will not be given these special triangles. You will need to include them for many problems as a part of your solution if you're looking for full marks. Now, we can use these two ideas. The two ideas that the cosine of theta is equal to the x coordinate, the sine of theta is equal to my y coordinate, and our special triangles to come up with coordinates for points around our unit circle. So we'll work here. We'll start off with our pi over 6. All right, so we're going to, now I've actually deleted my unit circle so you folks could read it a little better, but we're assuming some sort of a circle around like this. I do find it kind of clogs up my notes as you folks are watching, but we're assuming for every single point, for every single arrow, we're considering the point at the end to be one radius, 1 unit away from the origin. So let's consider this point right here, and we want to try and find the coordinates of this point right here. Like we said, we're taking advantage of the relationship that our x and y coordinates are equal to the cosine of theta, the cosine of theta and the sine of theta. All right, if that's the case, then first of all, I need a theta in here. So if I'm giving a theta, I know my theta should be somewhere like this. Fantastic. All right, now that's all well and great, but I don't really have a triangle here to work with. So I'm going to need to create a triangle right down here. I'll go straight down from this coordinate. This way, like we've already discussed, my y coordinate is equal to the opposite side of this triangle. My x coordinate is equal to my adjacent side of the triangle. And with the triangle set up like this, what we're doing is we're trying to say, okay, well, this angle right here, what angle is this? It's pi over 6. We already found that in a previous lesson. Okay, so if I'm working with pi over 6, I need to find my adjacent side to pi over 6 in order to find my x coordinate. I need to find my opposite side to pi over 6 if I'm going to find my y coordinate. So I'm working here. Okay, so the cosine of theta, let's see right here. The cosine of theta is equal to x. The cosine of theta for this triangle, remember, theta is equal to pi over 6. So I'm trying to find the cosine of pi over 6, and then I'll be trying to find the sine of pi over 6. Hang on. I know how to evaluate both of those. So we'll head over here. Pi over 6. Okay, so the cosine of pi over 6, I know I'm working with my adjacent side over the hypotenuse. So I'm working here with my adjacent side, square root of 3 over the hypotenuse. So I'm working here with the square root of 3 over 2. Square root of 3 over 2, good. Then I'm working with the sine of pi over 6, and here I'm working with my opposite side over the hypotenuse. I'm working with 1 over 2. Fantastic. So what that means, and this is the key here, what that means is the coordinates of this point right here. The coordinates of this point right here are root 3 over 2 and 1 over 2. Now, if you followed, fantastic. If not, then we'll practice the next couple together here. So we'll work with pi over 4 then. All right, well, now our triangle looks something like this. We have the right angle right here. Our theta is not pi over 6. This time our theta is pi over 4. Again, our xy coordinates are equal to the cosine of theta and the sine of theta. So if I'm working up here, okay, so xy is equal to the cosine of theta. Well, the cosine of pi over 4, that's what I'm evaluating here. Okay, so the cosine of pi over 4. And then I'll be evaluating the sine of pi over 4. All right, fantastic. And you know what? I'm just going to move that up to give me a little bit more space here. We should be able to evaluate the cosine of pi over 4 and the sine of pi over 4 by using our special triangles. So you know what? What I'll ask you to do is try to evaluate those on your own. Pause the video, try that out, unpause it when you come back. And we should be working with 1 over root 2 for both. That's right. In this case, the x coordinate is equal to the y coordinate. Both of them are equal to 1 over root 2. Now, we could rationalize those. So you may see those answers in your textbook as the square root of 2 divided by 2 for each coordinate. And that's great. And if you give your answer like that, that's fine. While we're working with the unit circle, I do think it gives a little bit more context. If you prefer to leave it in this form, not rationalized, I will allow that for this chapter specifically when we're working with the unit circle. Now, that does not mean all of our final answers in this chapter we're allowed to leave unrationalized in this state right here, but it does mean that if we're specifically working at the unit circle, I think if you find it more helpful to leave it with your square root in the denominator, I will certainly allow that. Now, what I'll ask you to do is fill in the rest, or the final coordinates in our first quadrant. So try that out. We're going to work with x, y right here. We know, again, that's equal to the cosine of theta and the sine of theta. And in this case, that's the cosine of pi over 3 and the sine of pi over 3. Try that out. Pause the video, try it out, and come back to unpause it when you've done it. And we should be working here. These coordinates are 1 over 2 and the square root of 3 over 2. Now, I understand my unit circle right now. It's really messy. It's filled up with all of our work. That's okay. I'm going to leave that there so that future you, when you come back to this note, you'll be able to see how we accomplished what we did. Now, if we've done as much as we've done so far, we could, if we wanted to, we could continue with this as we worked into quadrant 2. And we could evaluate our special angles for all of these points in quadrant 2, and then in quadrant 3, and then in quadrant 4. Now you might say, okay, hang on, Mr. Pasatka, that seems like an awful lot of work. And you know what? It is. If you want to go ahead and do that, by all means, go for it. Double check your work. In this case, as we get over to this side here into quadrant 2, you'll notice that instead of a theta, we'll be using alpha. We'll be using a related acute angle over here because that's what would be used to create a triangle. But either way, as we work through here, then we could actually pause for a moment and we could consider the idea of symmetry. So this here, obviously, we have, I'm not sure if you can tell, but Mr. Pasatka is incredible at drawing a perfect circle. So that is a perfect circle right here. And what we know with a perfect circle, if it's centered on the origin, is it has symmetry at play. So this coordinate right here, this point right here that we've already determined our coordinates for, has the same y coordinate as this guy over here. So we could actually come up with our y coordinate already without sketching our special triangles, without referring to our sketches up above, without analyzing them. We could come up with our y coordinate right away. Our y coordinate here is the square root of 3 over 2. Good job, us. Okay, you should be able then to find the y coordinate of this next guy and of this point. In fact, you should be able to find the y coordinate of all 3 of those points. All right, if you've done that, great job. We can actually work a little bit further because according to the symmetry of our circle, this x coordinate will be the opposite x coordinate of that, or rather the negative y coordinate over x coordinate over here. So if we were working with 1 over 2, now we're working with the x coordinate of negative 1 over 2. And I'm hoping you've seen the pattern that we're using in here. In fact, these 4 points right here will share the same coordinates with different signs. We notice as we work into quadrant 3 right here, we're expecting both our x coordinates and our y coordinates to be negative because in this quadrant, we're working to the left side of our y-axis, so our x coordinate is negative, and we're working below our x-axis, so our y coordinate is negative. So we can fill that in right here. We're working with negative 1 over 2 and negative the square root of 3 over 2. Fantastic. Then you should be able to fill in right here. We're working with positive 1 over 2 and negative the square root of 3 over 2. Nice and easy. It fills out. We're taking advantage of symmetry. So we can look a little bit further and we can see, okay, well, if those 4 points share the same coordinates with different signs, then these 4 points will share the same coordinates with different signs. So try that out. I know our sketch is becoming really full right here. That's okay. I'll ask you folks to fill in the coordinates for all of the points along our unit circle right now. The only lines that we're leaving blank for now are the purple lines, and that is at 0, at pi over 2, at pi, 3 pi over 2, and at 2 pi over here. We'll leave all of those blank, and I'll ask you folks to pause the video, fill those in, and unpause it when you're ready. Alrighty, so we have the rest of our, oops, it disappeared there. We have the rest of our coordinates here. You can double check your work with mine. Those missing ones that we're waiting on here, those come from what we call our quadrantal angles. And I'll write that out, quadrantal angles. Now, these angles are each obviously 90 degrees further than the previous one from one another. Now, if we're trying to come up with the coordinates here, it's actually even simpler than you think. Because if you remember, what we're working with here is a unit circle. And a unit circle has a radius of 1 unit. And if our unit circle has a radius of 1 unit, then the coordinates we're working with here, we already know the y coordinate 0. The x coordinate then that we're working with is a positive 1. Fantastic. We can use that same logic to come up with the coordinates for each of the other quadrantal angles. I encourage you to pause the video, figure them out, and double check your work. So working here, we have 0, 1 at our pi over 2 angle. We have negative 1, 0 at our pi angle. At 3 pi over 2, we have 0, negative 1. Fantastic. All of those nice and straightforward. Now we can push on forward. Okay, so the idea here is to come up with, remember, a function. And if we're coming up with a function right here, then it's our goal. Okay, so if we're working with f at x is equal to the sine of, or sorry, f at theta is equal to the sine of theta, then our horizontal axis right here, I know you're used to working with x. In this particular case, what we're working with is theta. Now what we're working with in the vertical side, we can call that, I'd rather not call it y. Really, it's the vertical coordinate. That is what our function is, right? So we're working with here the sine of theta. So at each point, each coordinate, what we're looking for, our horizontal coordinate is theta, our vertical coordinate is the sine of theta. So we head up here and we say, okay, well, let's take advantage. Okay, we know that the sine of theta, we know that x, y, as we've written a number of times through this note, x and y is equal to the cosine of theta and the sine of theta. So coming from that, that tells me that x is equal to the cosine of theta, which we already knew. Y is equal to the sine of theta. So we'll take advantage of this relationship, and as we work through, what we're looking to compare are the y coordinates from up above, because that's the sine of theta, along with theta itself. So if theta is equal to 0, then our y coordinate here, and I realize there's a lot to look at here. Maybe I'll bring out the highlighter. If theta is equal to 0, then my y coordinate is 0. If theta is equal to pi over 6, my y coordinate is 1 over 2. That's what I'm going to be plotting down here. So let's plot both of those points. Okay, so our first point right here, if our theta is equal to 0, y is equal to 0. Our sine of theta is equal to 0. So that point right here is at 0, 0. The next point, if theta is equal to pi over, pi over 6, then our y is equal to 1 over 2. So we need, okay, and here we need pi over 6. Well, that's going to be half of pi over 3. So I'll work with here pi over 6, and I'm working with 1 over 2. All right, there we go. There's our second point. We can head along and we can plot even more. All right, so if theta is equal to pi over 4, then our y coordinate is equal to 1 over root 2. If I'd like, I can throw that into my calculator right here. And I'm working with here 0.71. Okay, so 0.71. I'm working with, first of all, it's 1 over 4. So 1 over 4 would fall about here, pi over 4. And 0.71, 0.75 is here, so 0.71 right about there. Fantastic. And then, okay, I'm working up here. My next theta is pi over 3. And my next y coordinate is the square root of 3 over 2. So I can throw that into my calculator as well. The square root of 3 divided by 2. Nice and easy. I'm working with here 0.87. Okay, well, I can work with 0.87, so I'm working here pi over 3, 0.87. I'm getting closer to 1, but I'm not quite at 1 yet. Right around here. And then lastly, I know when I'm working here with pi over 2, then I have my y coordinate of 1. Okay, pi over 2, my y coordinate of 1. I'm working right about here. Now, something to pay attention to as we work forward, we don't have a theta value for every single pi over 6 piece in here, right? So it's not like we're plotting these, points with a consistent horizontal spread. So we need to make sure we're very careful right here. Now, using this, oops, that's pi over 2. Using this same logic, what I would like you folks to do is plot the points along for one entire period. And that is all the way from 0 until 2 pi. You're using our unit circle. You're using the y coordinates of our unit circle. You might find it beneficial here. Highlight all of your y coordinates, because remember, all of your y coordinates, they represent the sine of theta for any given theta. So I'll highlight these y coordinates. We're using these y coordinates to come up with this graph. I'll say try that out, fill in one full period, and then unpause your video to check your work. And we should end up with a general shape like this. Now, again, this is the shape that we were expecting. This is the shape that we predicted, that we already found when you were working in grade 11. This is the shape that comes when you plot the x coordinate along with, or sorry, the y coordinate of your unit circle along with the angle around. So when we're working here now, obviously this is a function. It's a full function. I know we have some points, but it is a full function in between. So we'll need to be a little bit careful. Here when we're plotting, obviously we want to fill it in with a nice, smooth, natural curve. So we're looking at something like this. I'm right-handed, my hand's in the way of my screen a little bit. Now, and we know we could keep going. If we wanted to, we could keep going and find more angles just by going more than one full rotation around our circle. In fact, we could keep going an infinite number of times around our circle. If you want a headache, keep looking at that and try that out. Or instead, if you don't want a headache, whoops, what we could do is we could work here, and there we are, we're trying to, fantastic, is we could go in the opposite direction. We could work with negative theta values, and we could head in a clockwise direction around here. Either way, in both directions, there are an infinite number of values that we can use. And what I'm getting at here is that we're going to expect our function to continue beyond where it was. We expect it to continue and to repeat forever in both directions. This is our sine function. This is our sine function plotted using radians. Now, we can use 5 key points if we would like. We can call them anchor points. And these anchor points we can use where y is equal to plus or minus 1, or where y is equal to 0, just to come up with a nice rough sketch of this function. So where we're looking here, y is equal to 0, y is equal to plus 1, y is equal to 0, y is equal to negative 1, and then y is equal to 0. We expect this pattern to continue ad nauseum. It will keep on continuing as long as we care to look at our sine function. It will go up, down, down, up, down, down, up, forever and ever in either direction. So if that's the case, we can take advantage of that pattern. We can come up with a nice general rough sketch of our function here. We're working here. Okay, we have a vertical axis. We have a horizontal axis. Yes, this is rough. That's okay. That's by design. So we're working here. And we have, okay, so we're expecting, first of all, we need to put the values in for plus or minus 1. Those are the y values. We know 0 is already in there. And then we're going to need some points on our horizontal axis. So we know, first of all, that a full way around a circle is 2 pi radians. So that's going to be 1 period of this function. And we could see 2 pi radians. It ends up right here. Now we know halfway between 2 pi radians is going to be a significant point. We also realize that halfway between this halfway point in our beginning, another significant point. So what we're putting down right here, you might recognize as our quadrantal angles. So we take advantage of these quadrantal angles. That's where we're expecting the points. That's where we're expecting to have 0, and then we go up to 1, and then we go down to 0, and then we go down to negative 1, and then we go up to 0. And we can see this general shape. Now, and I cannot emphasize this enough, the general shape of this function is not what we call a sawtooth. It does not have right angles or sharp turns involved. The sinusoidal function is a nice, smooth, natural curve. So when you are sketching your sinusoidal function, if it looks like that, you will lose a mark. If your curve looks like this, oh, better round it, and then you come down here, and then you think, oh, better round it, you round it smoothly, that is not a nice, beautiful sinusoidal curve. This, what you're seeing right now, is not a sinusoidal function. It needs to be nice, smooth, and calm. So if you're coming up with a nice, smooth, calm sinusoidal curve, I can walk you through that a little bit. You don't need to be a master of art. In fact, maybe you've clued in that you can accomplish math without being a master of art just from following along with our working class. But when we're working here, the idea is I'm going to just put in a few targets here. So I'm going to work, okay, a little bit before my points at plus or minus 1, I'm just going to put a little bit of an x. So bear with me. That x is what my mind is looking at as I'm going to sketch this curve. Okay, so when I'm sketching this curve, first of all, I start obviously at the origin. And I'll start here, and I'm going to aim for that x until I get about halfway there. Then I'll start smoothing it out. and then I repeat that. Okay, so I come through at a pretty sharp, sharply declining function right here. And then I go down and I aim before that, before this minimum is where I'm aiming here. And you can see I'm coming up with a nice, smooth, calm function. That's what we're looking at here. I need to see that shape. Do you need to draw those X's in? No, absolutely not. But if you're giving me the sketch of a sinusoidal curve on an assessment, then I need to see a curve. It needs to be smooth. It needs to be nice and calm looking, something like so. Fantastic, folks. Now we're going to go about and we're going to do that exact same process, but working with the cosine of theta instead. So we need the cosine of theta on our vertical axis. We need theta on our horizontal axis. Now, if we go back, if we remember how we came up with the coordinates for these points on our first function, we took them right from our unit circle. We took them from the coordinates of the points on our unit circle. What we did is we took them from the vertical coordinates on our unit circle because we knew that y is equal to the sine of theta. And if we knew that the y is equal to the sine of theta, fantastic, good job us. Now we're going to work with x, which is equal to the cosine of theta. So if you have a highlighter, you can highlight all of the x coordinates of our points way up here. It's these x coordinates that we'll be using in order to come up with our sketch. Fantastic job us. I realize I apologize for some of these x coordinates that are written in green and highlighted in green, but you know what? I am committed at this point. Alrighty, so from there we should be able to fill in our points. We should be able to fill in the point, and you know what? I'll ask you folks, try it out on your own. Pause the video here, try to fill in all of the points. Again, our period is going to be all the way to theta is equal to 2 pi. Try and fill in your points, and then once you've done so for one full period, unpause the video and check your work. So we're working here. We can see the general shape we were expecting to find, and again, we need to keep in mind what we're working with here is a natural, calm, smooth curve. Right now, again, I'm right-handed, so my hand's getting in the way as I sketch this here, as I try to sketch this here. There we are. Oh my goodness, we'll take one more attempt at it. And if it doesn't work, that's okay. We will we'll fix it before submitting. Now, where we're working right here, again, we need to recognize that our curve does continue in both directions. So you folks are responsible. If you're including this on a summative, you need arrows on the ends. These arrows do not imply that the function heads off in that direction forever. These arrows imply that the pattern that we're seeing continues forever. And that, in fact, is what happens with your cosine function. So we have our cosine function. It looks like this. Again, we can use our 5 what we call anchor points where y is equal to plus or minus 1 or where y is equal to 0 to come up with a nice rough sketch of the function. So actually, I'll encourage you folks to come up with that rough sketch on your own. Please make sure, just like we did last time, we're labeling our x-axis and our y-axis, our horizontal and our vertical axes right here. So I'll encourage you, pause the video, come up with your sketch, and then unpause. And here we have, again, a nice, smooth, calm curve. That's what we're looking for. That's what we are expecting. In this case, our pattern's a little bit different. In fact, it's the same pattern, just shifted over a little bit. But here we're working, we start off at 1, where our theta equals 0. Then our cosine of theta equals 1. So it goes 1, 0, negative 1, 0, positive 1. And that pattern will continue forever. Fantastic. Those are the shapes we're looking for. Now, if we would like to be honest, we can take a little bit of a, we can go forward with a little bit of flexibility here, folks. If you would like to spend some time exploring your tangent function, you can do so right here. We'll take a little bit more, we might come back to this in the future, but the one thing that you need to keep in mind is that your tangent function at all points is equal to the sine of theta divided by the cosine of theta. And if that's the case at any point, if we know the sine of pi over 4 is, say, 1 over root 2, and we know the cosine of pi over 4 is, say, 1 over root 2, then our tangent of theta will be 1 over root 2 divided by 1 over root 2. That equals 1. So I encourage you folks, you know what, at this point, unpause the, I'll actually pause the video and attempt to fill this in, because you should be able to handle something like this. Well, there will be a few points to speak about after you fill it in here. Good, so filled in, it should look something like this. And here where we're really going to zero in are where the cosine of theta equals 0 and where the sine of theta equals 0. So we'll look here first. Remember, a tangent function is in itself, it's a fraction. And if it's a fraction, then if ever our numerator is equal to 0, remember our numerator is the sine of theta. If ever our numerator is equal to 0, then we're expecting our function to equal 0. And we can see that pattern playing out. Wherever the sine of theta is equal to 0, then the tangent of theta will also be equal to 0. Fantastic. Okay, well then if that's the case, let's take a look at the cosine of theta. Wherever the cosine of theta is equal to 0, then our fraction will be 1 divided by 0. 1 divided by 0 is not a fraction we can evaluate. In fact, that, by definition, does not exist. It is undefined. So wherever we see the cosine of theta is equal to 0, then we're expecting our tangent function to be undefined. Fantastic. I encourage you folks to take a look at f of x is equal to the tangent of theta on Desmos, and we'll play around a little bit. I think we're doing okay. I realize this video is getting a little bit long, but I think we're going to discuss a little bit more next lesson, specifically some new terminology to describe the shapes of these functions. It should be a review from grade 11, but either way, we'll be working with our periods, amplitudes, and a little bit more. So nice work today, folks. At this point, you should be able to handle all of the homework for the 6.3 problems.